Chapter 15, Stationary Waves, Learning Outcomes. You should be able to demonstrate and explain the formation of stationary waves. Stationary waves are also called standing waves. So we will see how we can form stationary waves using some apparatus. Actually, if you check online, there are so many videos of how to form a stationary wave. Identify nodes and antinodes on a stationary wave. Determine the wavelength of sound waves using stationary waves. So we have nodes and antinodes. We will see the details. And at the node, the displacement is 0 always. Now, once you have a stationary wave, if it's a node, that point won't move. Okay, say for example, you have a stationary wave on a rope. So the points where the displacement is 0, where it is remaining as at that same place, that is a node. And at the antinodes, the displacement is maximum. Determine the wavelength of sound waves using stationary waves. Alright, so here are the topics. From moving to stationary, nodes and antinodes, formation of stationary waves, determining the wavelength and speed of sound, and then finally the summary. Okay, we'll have a quick look at the summary also, so you have an idea of what we are going to cover in this chapter. Stationary waves are formed when two identical waves traveling in opposite directions meet and superpose. Now, in the exam papers, they have asked how a stationary wave is formed. Okay, so you should know this. In paper 2, they are asking how is a stationary wave formed. So you have to write it like this: opposite directions, identical waves, that means they will have the same frequency, wavelength and all. Then they superpose. These are some of the keywords. This usually happens when one wave is a reflection of the other. So you send a wave, it gets reflected, and you still keep sending waves. So what happens is the reflected waves and the waves that are sent superpose, because they are, once it gets reflected, it will be traveling in the opposite direction to its original direction. A stationary wave has a characteristic pattern of nodes and antinodes. A node is a point where the amplitude is always 0. I mentioned this. And antinode is a point of maximum amplitude. Adjacent nodes or adjacent antinodes are separated by a distance equal to half a wavelength. Now for this, I have also created a handout, and in this handout we will learn about the path difference or phase difference of standing waves, and it is different from the phase difference or path difference for progressive waves. Okay, here we are talking about standing waves or stationary waves. And then we can use the equation V equals F lambda. This is a very famous wave equation to determine the speed V or the frequency F of a progressive wave. The wavelength lambda is found using the nodes or antinodes of the stationary wave pattern. Okay, so let's go to the beginning. From moving to stationary, so the wave that moves or transfers energy from one place to another is a progressive wave. The waves we have considered so far in chapter 13 and chapter 14 have been progressive waves. Okay, you can see it's in black bold letters, which means you have to know the meaning of that. And you can see even this word here, stationary wave, also called standing wave, is in green bold letters. So whatever in this book that is in green bold letters is very important. You have to know the meaning with understanding, and if you look at the glossary, the meanings of these words are given at the in the last few pages of this book. There is a glossary with the meanings of these words, because in paper 2 and also in paper 4 they can ask you to write the meaning of this. For example, what is a stationary wave? How is a stationary wave formed? Let's see. A second, okay, so they start from a source and travel outwards, that is a progressive wave, transferring energy from one place to another. A second important class of waves is stationary waves, also called standing waves. These can be observed as follows. Now you can use a slinky to create stationary waves. Okay, and in our list of demonstration videos also you can check the video for how stationary waves are formed. Okay, using a slinky we can create a stationary wave. I will upload that video also soon, and how a stationary wave is formed using a slinky. We have done this practically in our classes here. Okay, these can be observed as follows. Use a long spring or slinky spring. A long rope or piece of rubber tubing will also do. Lay it on the floor and fix one end firmly. So what we do is we have this slinky, and then one student holds it from the other side, the other person will move it sideways to produce the stationary wave. Move the other end from side to side so that the transverse wave travel along the length of the spring. Using the slinky, you have learned how to form transverse waves and longitudinal waves. And already we have uploaded videos for that, showing how the transverse waves are formed using the slinky, and also how the longitudinal waves are formed using the slinky with the explanation. You can watch those videos. Then here we are creating a transverse wave. Now what happens is that transverse wave goes, it hits the fixed end, see like this, the fixed end, and then it gets reflected. Now you are still sending the wave. So what happens? The reflected waves and the waves that are still being sent, they interact, they superpose to produce the standing wave. And for this to happen, the waves should have the same frequency. They should be identical waves. Move the other end from side to side so that the transverse wave travels along the length of the spring and reflect off the fixed end, figure 15.2. If you adjust the frequency of the shaking, you will be able to achieve a stable pattern like the one shown in figure 15.3. This is the one. Alter the frequency in order to achieve one of the other patterns. You should notice that you have to move the end of the spring with just the right frequency to get one of these interesting patterns. The pattern disappears when the frequency of the shaking of the free end of the spring is slightly increased or decreased. Okay, so there are so many videos online, you can check on how these waves are created, how to produce stationary waves. Because in this chapter you have to see a lot of animations. Waves, you can't just look at it in 2D and learn it very well. You have to watch the 3D animations, you have to watch the videos, you have to, if you can watch the videos, that's fine. It's like actually being in a practical class if you can watch the video, because in the video demonstration you can also slow it down, you can rewind, you can listen the explanation again. So make sure you watch a number of videos on how stationary waves are formed, and not only stationary waves, even for the other wave chapters about superposition, about transverse wave, longitudinal wave, different types of waves. A slinky spring is used to generate a stationary wave pattern. Different stationary wave patterns are possible depending on the frequency of vibration. So here is the fixed end, here is the free end. Now in the case of the slinky, this end is fixed, so one student will be holding this end firm without moving it. Then the other student will be moving it like this. So the slinky is on the floor. Now this is from the top. You are looking at the floor from the top. So this is the slinky lying on the floor. So you move it like this, then what happens? The wave is going like that, it gets reflected, and it produces a stationary wave like this. Now you will notice that there are points that don't move, like this point here, this point, and this point. So what happens? What you will notice is this part moving up and down, this part moving like this, up and down, up and down. So here and here it is fixed. So here you can see the amplitude is maximum. That is called an antinode. And at the node, the displacement is 0. Here the displacement is maximum. Okay, now we will learn about nodes and antinodes. What you have observed in a stationary wave on the long spring, there are points along the spring that remain almost motionless, while points on the either sides are oscillating with greatest amplitude. Now, like I said, to understand this, you have to see the demonstration, or you have to watch the video of how stationary waves are formed. Otherwise it's difficult, it may be difficult for you to understand this. Let's look at the animation to help you understand this better. Okay, over here we have a fixed end, so I have selected fixed end over here. Then I will click these two also so that you can see the incident wave. Let's start the animation. So what happens is, this is what happens. So you have the microwave, which is an electromagnetic wave coming like this. Okay, here is the trough, here crest, here is the trough. So this is the electromagnetic wave coming, the microwave coming towards the hard end, the wall. Now what happens is, once it hits this fixed end, the hard end,
it will get reflected. So here you see the blue wave is the reflected wave. Now what happens is, as a result of the incident waves and the reflected waves superposing, you can see what happens is you get this resultant wave. Okay, what you see in black, after the two waves, the incident wave and the reflected wave get together, what you get is the resultant wave. And I can show you only the resultant wave. I can remove the incident wave and the reflected wave from this animation. So what we have here is a standing wave, and these points of zero amplitude are the nodes. Here we have the antinodes. Antinodes have the maximum displacement, the maximum amplitude. Okay, again I can show you the incident wave. That is the wave that is coming towards this wall, that is also in red. And the reflected wave also I can show you, that is the wave that gets reflected from this hard surface. So what happens is, the incident wave comes in and then it hits the hard surface, then you get the reflected blue wave, but the incident waves are still coming this way to the right. The incident waves are still moving to the right. The reflected waves are coming this way. So the incident wave goes, hits the wall, gets reflected, but still more and more red waves, the incident waves are coming, and more blue waves are going this way, the reflected waves are going this way. As a result, what will happen is they will merge. They will interact. The interaction causes what we call superposition. So if you are not familiar with what superposition is, you have to review that chapter on superposition. Okay, you have already learned how to draw the wave that is a result of superposition. Now let's have a look how we can do that over here. I will pause this right there. Okay, so what you do is, over here you have to you have to add the amplitudes of the two waves. The amplitude here of the red wave plus the amplitude of the blue wave will give you the amplitude of the black wave, which is the resultant wave. The result of these two is the resultant wave. Similarly, over here we have amplitude of the red wave positive, amplitude of the blue wave negative over here, but they are the same magnitude. So the result is let's say plus 1 millimeter, minus 1 millimeter. So over here it will be 0. Always at this point at the node, the amplitude is 0. Okay, I'll resume this again. Okay, let's take this situation over here. Again, you can see over here the red wave, the incident wave, and the blue wave, the reflected wave, have the same amplitude. So we double it, we add the two together, then you will get over here. So you have to add it vertically. You have to add it vertically, then you get the resultant wave. Okay, let's try that over here also. So let's say now here you can see this length from here to here.
Okay, so this was actually a past paper question that I solved, and it is explaining how the standing wave is formed using a wave that is sent and with its reflection. Okay, so you can see the solution to this past paper. Actually this paper, let me show you. Yeah, this is the paper, that is October-November 2010, paper 1, variant 2, question number 6. Okay, so for the full explanation you can watch that video. Now let's go back to the lesson. So like I said, you have to watch some videos to understand this. So this whole explanation is there in that video. Anyway, we'll quickly go through this bit. What you have observed is a stationary wave on the long spring. There are points along the spring that remain almost motionless, while points on either end are oscillating with greatest amplitude. The points that do not move are called the nodes. So you see, you should know the meaning of this word because it's in green bold letters. And the points where the spring oscillates with maximum amplitude are called the antinodes. At the same time, it is clear that the wave profile is not traveling along the length. So again, if you saw the animation, that standing wave, the points where you have nodes, it's not moving, but the antinodes, they will have maximum displacement, positive and also negative. At the same time, it is clear that the wave profile is not traveling along the length of the spring, that is a standing wave, hence we call it a stationary wave or standing wave. We normally represent a stationary wave by drawing the shape of the spring in its two extreme positions. Okay, this figure 15.4. Right, so this is figure 15.4. Now you can see here we have an antinode, here we have antinode, here we have a node. The fixed ends of a long spring must be nodes in the stationary wave pattern, and there are so many videos about this, so you can watch that, then you will have a better understanding. At the same time, it is clear that the wave profile is not traveling along the length of the spring, hence we call it a stationary or standing. We normally represent the stationary wave by drawing the shape of the spring in its two extreme positions. The spring appears as a series of loops separated by nodes. In this diagram, point A is moving downwards. At the same time, point B in the next loop is moving upwards. The phase difference between points A and B is 180 degrees. So, from here to here, the phase difference is 180 degrees. Now, to help you understand this better, I have a separate handout. We'll go through that also. Hence, the sections of springs in adjacent loops are always moving in antiphase. So, on either side of the node, now this is the node, on either side of the node, that means anywhere from here to here and from here to here, they will be antiphase. The phase difference is 180 degrees. Don't confuse this with the phase difference or path difference with stationary waves. Progressive waves. For progressive waves, it is different compared to stationary waves. This is a common mistake that students make. Hence, the sections of spring in adjacent loops are always moving in antiphase. They are half a cycle out of phase with one another. So, it's lambda. Okay. So, anywhere from here to here, any point from here to here and any point from here to here will have a phase difference of 180 degrees or a path difference of lambda. Remember, path difference is given in terms of wavelength, lambda. Phase difference is given in terms of angle, either degrees or radians. Okay, so formation of stationary waves, you already watched the video. Okay, so I'm not going to go through this part again. Where you have nodes is where there is destructive interference. Where you have antinode is where you have constructive interference. Okay, so remember that video, you can watch. There are several other videos also. So what happens is the wave is sent, it gets reflected. Now when the trough of the reflected wave and the crest of the wave that is sent is still being sent, superpose, when they come together, you will get destructive interference because you have positive amplitude and negative amplitude of the same magnitude adding together. Then if you have the crest and the crest, or the trough and the trough of the reflected wave and the wave that is sent superposing, then you will have constructive interference. At that point you will have an antinode. So that is what is explained here. Now you can see the black dots and the black dot and the cross. So these are 2 points you can see when it is moving, and you have the red wave and the blue wave, and the resultant wave is the green wave. Okay, the green wave is the resultant. So you can see here it's both together, so you will have something like that. Now when this moves to the right, and see, this is the reflected wave, the red one. The blue one is the wave that is being sent from this end by moving the hand or by moving the object. Then again you can see here, again we are using the methods that we used to add the waves in the previous chapter on superposition. So even in that past paper example also I am explaining it. Now what happens here, you can see trough and crest meet. So what happens, the resultant is 0. So this is how we have a standing wave. So in the standing wave, what you will see is this going up, down. Here it is fixed, here going up and down, something like this. Alright, so here you can see this one. Now we'll have a look at the handout so that you can understand this better. If you want this handout, you can follow the instructions in the description. So let's go through. Sometimes waves appear to be standing, that is the crest and the trough appear to stay in the same place. We can see them in water, especially water surrounded by walls. We call them standing waves or stationary waves. Any kind of wave can form a standing wave. So you see, musical instruments depend on standing waves. Stationary waves are formed when two progressive waves are superposed. So this is what is needed to form a stationary wave. equal frequency, nearly the same amplitude, same speed. So if the frequency and the speed are same, then according to V equals F lambda, the wavelength will also be the same. So they are actually identical waves, we can say, and they have to be traveling in opposite directions. So here, if it's a hard surface, this is what will happen. Again, you saw the video, the animation, right? So let's go back to the last part. Okay, this is a very important part. Comparing standing waves with progressive waves. For all standing wave patterns, these 2 points are true. The amplitude varies according to the position from 0 at a node to maximum at an antinode. So at the antinode, the amplitude is maximum. The amplitude of a given point is always the same, because in the stationary wave at a certain point that amplitude is the same, but where you have so the phase difference between two particles is 0 if the points are between adjacent nodes. This is what I mentioned previously. It is 180 degrees if they are either side of a node. Okay, so what that means is, if you take this point and this any point from here to here and any point from here to here, what happens is, when this part moves up, let's say this is a rope, standing wave in a rope, when this part moves up, this also moves up at the same time. But when this moves up, if you consider any point from here to here, when this moves up, this points also move down. So what we can say is P and R are antiphase. So is P and S, Q and R, Q and S. Okay, so but if you take P or Q and T or U, so here and here they are in phase, because as soon as this moves up, this also moves up. That's what they mean by this. The phase difference between two particles is 0 if the points are between adjacent nodes. So any point between two nodes is also the same. So here is one node, here is another node. Between this also, as soon as this moves up, this also moves up. But it is 180 degrees if they are either side of a node. So here is the node on either side, then they are having a phase difference of 180 degrees. Because when this moves up, this will move down. So this whole thing here between the two nodes moves up together. So that's why any 2 points between nodes, for example P and Q, they will have a phase difference of 0. Okay, so you have to go through this to understand it better. Now stationary waves, phase is n pi radians, where n is the number of nodes between the 2 points. So if the number of nodes between the 2 points is 1, so that is, let's say this and this, so between these 2 points it's 1, so then they will have a phase difference of pi radians, so 180 degrees. See, if this is 1, then if it is 2, if there are 2 nodes between the points, for example let's take Q and T, so between the points Q and T there are 2 nodes, so they will be in phase. Okay, because as soon as this moves down, this also moves down. So let's see. So if it's 2, it will be 2 pi radians or 360 degrees, which is the same as 0 radians or 0 degrees. They are in phase, where n is the number of nodes between the points. So remember this, phase difference between 2 points for stationary waves. Okay, let's continue. So actually that is what is explained here. All this explanation is for that. And here you can see separation between 2 adjacent nodes or between 2 adjacent antinodes. So between 2 nodes or antinodes, it's pi over 2. Okay, let's have a look at the diagram again. Between 2 nodes or 2 antinodes. Alright, so if this is confusing, just stick to what I explained. Okay, that's easier to understand. Okay, so here we have a comparison, just similar to here also we had a comparison. Frequency, all particles vibrate at the same frequency except at the node where there is no vibration, that is for stationary waves. But progressive waves, all particles vibrate at the same frequency throughout the wave. amplitude varies between 0 at the node and maximum at the antinode. Remember, stationary wave, there will be between the nodes, it's moving up like up and down, right? Like that. We saw in the case of a rope. At the antinodes, S will vibrate at a bigger amplitude to R. S will vibrate with a bigger amplitude to R. Can you see it will move all the way here? Here it goes only up to this point. So S will have a greater amplitude compared to R. At a bigger amplitude compared to R. Now again, don't confuse this with the displacement also. Okay, again something common, because this is a standing wave. Okay, so each point is like separate, we can say. Now again, you might think, okay, displacement like what I explained, but actually it is the amplitude. Okay, because these are like, it is not a progressive wave, it's a stationary wave. Then the amplitude is the same for all the particles. Now here it's okay, right? It's the same for all the particles, and this already I explained. So be careful, it's very confusing at times. So remember, here it's the amplitude. Any point you take, we consider the amplitude, because if you consider this point R, it will move all the way up to here, from here then again all the way up to here. So its maximum, its amplitude is here. Now the amplitude of R is less than the amplitude of S, because S will move from here all the way to here, and also from here all the way up there. So that will be the amplitude of S. Okay, then observing stationary waves. Okay, there is a video for this online, you can check, right? We over here, I mean, I can, if you Google it, you can see the video. Okay, exact same thing is there online. All right, so let's see. Observing stationary waves continued. This okay, so again all these details, Melday's experiment. Again, for this also there are videos online. You have to see the video to understand it, and so make sure you watch that, then you will have a better understanding. Alright, so here what we are doing is we have a tuning fork. Now a certain tuning fork will vibrate at that particular frequency. So we have different tuning forks with different frequencies. So if you take just one tuning fork, it will vibrate at a particular frequency. So the sound, the waves that it produces, in the case it can be sound waves, actually, yeah, the sound waves it produces. Now those sound waves we may be able to hear or we may not be able to hear. If it's within our audible range from 20 to 20,000 hertz, then we will be able to hear it, otherwise we won't be able to hear it. So when you hit these parts of the prongs, okay, these two parts are called the prongs of the tuning fork. This is the stem. So if you hit the prongs on something like a gong, what will happen is the prongs vibrate at the frequency that this tuning fork is made to vibrate. So what you do is you place it on top of a hollow tube like this. Now the tube is hollow and it's open at both ends, here and here. And here we can see we have a measuring cylinder with water filled. Now what happens is when you lower this pipe, let's say this pipe with both ends open or tube with both ends open, you lower it with the tuning fork right above it. And what happens is the length of the air column changes. So if you move this tube down, the length of the air column decreases. If you move it up, the length of the air column increases. Okay, so what happens is you can, if you move it down, so there will be a points where you will hear very loud sound. That is where resonance occurs. Okay, in the A2 lessons you will learn something about resonance. So that is when you have an antinode here and a node here. That's where you will hear maximum sound. So always remember, if you have a tube and if you are hearing a loud sound, always at the open end you will have an antinode. At the closed end you will have a node. Okay, so now this thing you can also do it with this, even with the microwaves. Okay, so what you have is the reflecting sheet. You can increase or decrease the frequency, or if you have a constant frequency, you can move this the emitter of the microwaves forwards, backwards. Okay, let's say you have you can adjust the frequency, and this is the reflecting sheet. So the microwaves get sent, they get reflected. Now that past paper question I did was a question on microwaves, something like this. So what happens is, once you have a standing wave created here, and if you move the probe along the line that is perpendicular to both the transmitter and the reflecting sheet, let's say you draw a line that is perpendicular, so you can see this part of the microwave transmitter and this reflecting sheet, they are parallel. Okay, so that means you can if you draw a line from the middle of this to that sheet, it will be a perpendicular line to both this part of the front part of the microwave transmitter and also the reflecting sheet. Now if you move the probe along that line, you will notice that at some places the reading is minimum, and at other places the reading is maximum. Now the reading is minimum where there is destructive interference or where there is a node. It is maximum where you have antinode, because the amplitude is maximum there, so the reading here will be maximum. So at the antinodes you have constructive interference where trough and trough meet, and trough and trough or crest and crest meet. Okay, so this is where we have resonance. Now all of that is explained here. Like I said, to understand this you will have to see the video, then you will have a better understanding. Okay, now this is what is happening. Now in this case, this is called resonance tube, because you will hear a loud sound when resonance occurs, which is when you have a node at the closed end and an antinode at the open end. Remember, always when resonance occurs, there will always be at the open end there will be an antinode. You can't have a node at the open end. At the closed end you will always have a node. You can't have an antinode at the closed end when resonance occurs, when you hear the loud sound. Okay, so now here we had Melday's experiment. There is a video online, you Google it, you can find it. Then for these also there should be videos. Now even using a past paper question, I explained something like this, microwave getting reflected. Then we have the resonance tube. Even for this there are so many videos online, you can check on YouTube to understand this better. Okay, this is called a resonance tube. And what happens is, now these are the possibilities. So let's say you start with the water level somewhere there. Okay, so you let's say you move start from the bottommost position and then you move it up slowly. So when it is at the bottommost position, so the longest wavelength, what you can get is this thing. You have a node, antinode here and a node here. Then when you move it down, when you increase the length of the air column here by moving this up, then the next possibility is this. Now here the frequency is not changing. So you see the wavelength here and the wavelength here are still the same, because the frequency is the same and the speed is the same. The frequency of the sound waves is fixed because we are using the same tuning fork. Okay, but here if you go through it, maybe we can change the frequency. Okay, anyway, let's see. So there are two ways actually. One is by changing the frequency until we hear a loud sound, which is where resonance occurs, or changing the air column. But here what we are doing is, the frequency of the waves is constant, we are changing the length of the air column. Okay, so what we will do is, now here it's longer. So I told you always at the node should be at the closed end. At the antinode, at the open end, you should have the antinode. So this is the first possibility. Then the second possibility is this. Now you can see the wavelength is still the same. Okay, this is quarter of a wavelength. So from here to here it's quarter of a wavelength. Then from here to here it's another quarter of a wavelength. Then from here to here another quarter of the wavelength. So in other words, this is 3/4 of a wavelength. You can see if you continue this all the way up to there, you have one whole wavelength. So this is 3/4 of a wavelength. Okay, so now remember, we are drawing it to look like a transverse wave, but sound wave is a longitudinal wave. So because it's easy, only we are doing it like this. But actually what is happening is, because it's a sound wave, a longitudinal wave, At the antinode you will have maximum amplitude of vibration, which is indicated by the arrows here. So actually it is this, but you can draw this because that will make it easy for you to understand. Now over here at the node, no vibration. Can you see no red arrows? And here also it's a node. See, no vibration. And can you see the arrows are longest at the antinode, where the amplitude of vibration is maximum. Okay, now this is a tube with one end closed, one end open. Air column where one end is closed, one end is open. Okay, so here this end is closed by the meniscus of water and the other end is open. So that is what we draw here, open, close. But if you look at another tube where both ends are open, then if you have resonance, always at the open end you should have antinode. Got it? Okay. Then make sure you answer all these questions. Okay. Then stationary waves and musical instruments. Now again this is very easy. Remember at the closed end, now what we saw before, both ends were fixed. This end is fixed, this end is fixed. So that means if it's fixed, it can't move up and down. It's a closed end. So at the closed end, we will always have a note. Similarly, if it's a musical instrument, the string is attached at the two ends. So you will have a note. Note here, note here. Then here what we are doing is we are changing the frequency. Now in this case also there are videos explaining this. Using the signal generator, we can change the frequency with which this vibrates, but we can't change the length. So here what we did, the frequency of vibration was constant, but we could change the length of the air column. But over here, the length is constant, but the frequency is changed until you get the standing waves of different frequencies. So you can have just one note here and a note here, then you can increase the frequency so that you get two notes, three notes like that. And that is what we are going to see now. You see over here, this is the first possibility where the wavelength is longest. See, from here to here it's half a wavelength. Okay, so lambda equals 2L, because from here to here it's half a wavelength. So we can also write this. This is L, length of string. L is what? Lambda over 2, because it's half a wavelength. So when you rearrange, then lambda equals 2L. Now we increase the frequency so that we get a note here. Now here no notes in the middle. So can you see, now you have one whole wave. Here you have only half a wavelength. Here you have one whole wavelength. So lambda equals L. Then here 1.5. So you have 1.5 wavelengths in this cell. 1.5 is what? 3 over 2. So we can also write L equals 3 over 2 lambda times lambda. This is the fundamental, or the very first one. Fundamental, you know the meaning of the word fundamental, basic. So the very first possibility, so it's called fundamental, where you have no nodes in between, just one antinode. Then second harmonic, where you have one node and two antinodes. So here we have one antinode, here we have two antinodes, here we have three. So like that you can continue. 4 antinodes, next one 5 antinodes, like this. Okay, so this is F0. Here the frequency is double. You can see the wave speed is the same, but the wavelength is now halved. See, this wavelength is half this wavelength. So if you halve the wavelength, V equals F lambda. So if you use that equation, V equals F lambda, if you halve the wavelength, the frequency will double. Okay, so we can even write it and show you. Okay, we have V equals F lambda. Okay, so what's wrong with this? Okay, so yeah, that's working. All right, so V equals F lambda, then F is equal to V over lambda. Now the speed of the sound waves, or the waves in the string is the same. V is constant. So if you decrease the wavelength, the frequency will double. Okay, so if you halve the wavelength, the frequency will double. If you decrease the wavelength, the frequency will increase. If you halve the wavelength, the frequency will double. So that's what is shown here. So here the frequency is F0. Here it is double. Here it is triple. Can you see? Here you have 2. Here you have 3. antinodes. Here you have only one antinode. You can even work it out and find it. Fundamental frequency is the minimum frequency of a standing wave for a given system or arrangement. It is important because this is the minimum possible you can get just with one antinode. Okay, then now again this drawing, they should actually draw it very close to the two ends. Can you see this distance is too far? This is okay. Even here it's drawn like this, but anyway you have the idea. Okay, at the closed end you will have a node. At the open end you will always have antinode. So this is the first possibility. Now here they are changing again the frequency. Can you see the length is constant, but we can change the frequency of the sound wave. So here you will hear a loud sound, here you will hear a loud sound, here also you will hear a loud sound. And here the string will vibrate with maximum amplitude, or in other words, you will get a standing wave here, and a standing wave here. Okay, so like that you can figure this also out. So from here to here, that is the L. L is quarter of a wavelength. L is lambda over 4. You can see it's a quarter of a wavelength. Or we can say lambda equals 4L. To form one whole wavelength, we need 4 L's of this. Here, L is 3 quarters. L is 3 lambda over 4. Then this one, 1.25, right? Or 5 over 4. Sorry, 1 and a quarter. One whole wavelength and a quarter. 5 over 4. 1.25. Yes, correct. So L is 1.25 lambda. 5 over 4 is 1.25, right? 5 over 4, 4 into 1.25. All right. So here you can see the frequency is here f naught. Here it will be 3 f naught. Here it will be 5 f naught. Now you can use the equation v equals f lambda and figure out the frequencies. Okay, even here you can figure it out using v equals f lambda. And so this is what you need to remember. F naught, 2 f naught, 3 f naught if both ends are closed, or if you have nodes at both ends. Same thing applies if you have antinode at both ends. Like for example over here, for this also, where both ends are open, where you have antinode on either end or node on either end, this will apply. So the fundamental is f naught, second harmonic is 2 f naught, third harmonic is 3 f naught. The first harmonic is called the fundamental. Now if one end is closed, other end is open, that means if you have a node at one end and the antinode at the other end, okay, then this is what you will have: f naught, 3 f naught, 5 f naught. So you see it's odd numbers here. Here it is the natural numbers. So if you know the fundamental frequency, then the frequency of the second harmonic is 2 times that. But over here the second harmonic is 3 times the f naught, the fundamental frequency. Here the third harmonic is 5 times the fundamental frequency. So remember, if we one end node, the other end antinode, one end closed, the other end open, one end fixed, the other end free, this is what you have to know. Okay, you can even figure it out by drawing a diagram. Now again you can see here a standing wave is formed, and in this standing wave this end is closed. Can you see? Closed. This end is open. Okay, so you just place the loudspeaker at the open end. It's open. So the loudspeaker is placed at the open end. Now if you, it's a hollow tube with one end closed, one end open. For example, like a measuring cylinder. If you place the measuring cylinder horizontally and keep the cone of the loudspeaker on this side, you don't close it. Okay, if you don't keep it all the way inside, you just place it a little bit outside so that there is a gap between the cone of the loudspeaker and the top part of the measuring cylinder. Okay, so this end is open, that's therefore you will have antinode. This end is closed, so you will have a node. You can adjust the frequency of the sound waves it produces using the signal generator. Signal generator is used to adjust the frequency. You can change the frequency using the signal generator. So the first possibility is what? Antinode here, node here with nothing in between. Okay, it's something like this. Like this. Antinode here, node here. So again, antinode here, node here. That is the fundamental. Okay, fundamental frequency, we can say f0. Then what we can do, so the first one is this, the fundamental. The second one is this. Okay, you have one node in the middle. Then the third one is two nodes in the middle. Here you have 1, 2, 3 nodes, which means it is the one after this. So then it will be 7 f0, odd numbers. Okay, 1, 3, 5, 7, 7 f0. So for this, it will be 7 times the fundamental frequency, because you have 1, 2, 3 antinodes in the middle. Here you have only 2. So that means the next one is 3 antinodes in the middle. So what you have to remember here is, if one end is open, one end is closed, the fundamental frequencies will be 1 f0, 3 f0, 5 f0, like that. But if both ends are closed, or if both ends are fixed, or even if both ends are open, or if both ends are free, that means if you have node on either end, or antinode, like this, antinode, or node, like this, node, then it will be f0, 1 f0, 2 f0, 3 f0, like that. These will be natural numbers. Okay, so this is very important. Now there are exam questions on this actually. Okay, then the rest is easy. You can go through it and understand it by yourself. Okay, here you can see reducing and eliminating errors using stationary sound waves to determine lambda and V. So this is self-explanatory, and this is about end correction. This also is very easy. You can understand it by yourself by going through this. Okay, then again the summary. Now I think you have a better understanding of this. How stationary waves are formed is very important. You should know that. In the exam paper they test you on this. So stationary wave has nodes and antinodes. Node is a point where the amplitude is 0. Antinode is a point where we have maximum amplitude. Adjacent nodes or adjacent antinodes are separated by a distance equal to half a wavelength. Okay, that's what we were going through earlier. So from one node to the next node, or one from one antinode to the next antinode, the distance is one wavelength, half a wavelength. Sorry. Okay. Wait. Yeah, half a wavelength. From one node to the next node, or from one antinode to the next antinode, the distance is half a wavelength. Let's quickly have a look at the diagram. Yeah, that's what they explained here. Between two adjacent nodes or antinodes is a separation between adjacent node and adjacent antinode. Okay, so again I think it's easier. Okay, here, right here, it's there. So from this node to this node, it is half a wavelength. From this antinode to this antinode, it's also half a wavelength. But if you go from a node to antinode, okay, so here let's say this is the node, to antinode it's quarter of a wavelength, or from antinode to a node it's quarter of a wavelength. That is what that point in the summary means. Let's go back to the summary quickly. Yeah, see, we can use the wave equation V equals f lambda to determine the speed V or the frequency f of a progressive wave. The wavelength lambda is found using the nodes or antinodes of the stationary wave pattern, because it is these progressive waves that form the stationary wave. Now when I discussed that past paper question, I explained that. So what happens is the progressive wave is sent, then it gets reflected, then the progressive waves that are still coming superpose with. So you have the waves, reflected waves having the same frequency, same wavelength, same speed as the progressive waves that are sent, because it's a reflection, but only difference is they are traveling in opposite directions. So if they are traveling in opposite direction, as if they superpose, it will create a standing wave. So the standing wave will also have the same frequency, same wavelength, same speed as the progressive waves which created it, but the amplitude will be different. Okay, Okay, so that's what this means. We can use the wave equation v equals f lambda to determine the speed v or the frequency f of a progressive wave. The wavelength lambda is found using the nodes or antinodes of the stationary wave pattern. So from one node to the next node, it is half a wavelength. From using that you can find the wavelength of the progressive wave. It will be same as that of the stationary wave. Okay, then again this point is very important. Stationary waves are formed when two identical waves traveling in opposite directions meet and superpose. This usually happens when one wave is a reflection of the other. Okay, it doesn't need to be reflection. Even if you have two waves of the same frequency, same wavelength traveling in opposite directions towards each other, once they meet, they will superpose to form the stationary wave. Okay, so that's the end of this chapter. Now you have to answer all the questions in these brown boxes and check the solution, because that way you will have the minimum knowledge required to answer the past paper questions. And once you finish that, you can start on this end of chapter questions and the past paper questions. Okay, using the PDFs that we have here, you can do the questions which are arranged by topic with the solutions after doing the questions in the brown boxes. And once you start that, you can even start this. And once you finish that, you do the questions in the past paper questions which don't have the solution. You do it like doing an exam, and then you can grade it by yourself. So this is the order. It's in increasing difficulty order of increasing difficulty. Okay, so here you can see some questions. Now you see vibrator. So this is the free end, because it moves up and down here, but here it's a fixed end. Okay, over here, yeah, so this is also moving up and down, vibrator. So this is the free end or open end. So here you will have it's fixed here, right? Yeah, it's fine. So here it's a node, here also it's a node. It's shown in the diagram. Okay, anyway, when you go through it, you will understand it, because already the stationary wave is created here. Okay, otherwise if this was a free end, then it's a different case. Okay, here it's open end. So always you get an antinode here. Here it's closed, you will get a node. So this happens when there is resonance. Always happens when there is resonance. Okay, so here again, so more questions. Make sure you do the questions, and make sure again you watch a lot of videos on these experiments especially, because for you to understand it better, you have to see demonstrations, you have to see videos, and go through the past paper questions that I've solved on waves, especially stationary waves and superposition. And make sure first thing you have to do is understand the theory well and answer the questions in these brown boxes. These kinds of questions, and then do the questions from the books that we have, the PDFs or the hard copies that we have of the past paper questions with the complete solutions. Then you can also do the end of chapter questions in this chapter, and finally you have to do the past paper questions, again arranged by topic. Do it like doing an exam. Okay, so that is the end of the chapter on stationary waves.